People out in the Palisades, Sunset, and Hearst burn zones are under evacuation warnings right now.
California's coastline has always been shaped by motion. Waves, tides, and weather have carved its cliffs for thousands of years. But what is unfolding now is different in both speed and scale. Across the state, roads that once seemed secure are cracking. Rail corridors built along scenic bluffs are bending and shifting. Entire chunks of cliff are collapsing into the ocean below, sometimes without warning, sometimes in rapid succession. These are not isolated accidents or the result of a single storm. Instead, they are signs of a system under sustained stress. Multiple stretches of coastline are failing within days of each other, drawing urgent attention from scientists, engineers, and emergency planners. At the heart of the concern is a simple reality. The forces acting on California's coast are aligning in ways that dramatically increase risk. Relentless storms, elevated ocean levels, and waterlogged ground are pushing already fragile landscapes toward a breaking point. For millions of people living, working, and traveling along the edge, the question is no longer whether the coast will change. It is how quickly and how suddenly that change will arrive. Chapter 1. When nature doesn't reset. In a typical year, winter storms arrive in cycles. Rain falls, rivers rise, and then the system clears, allowing the ground to drain and stabilize. This winter, that reset has not happened. Storm after storm has swept across California's coastline with little pause in between. Each new system adds more water to cliffs and slopes that are already saturated. Instead of drying, the ground remains heavy, weakened by moisture that penetrates deep into the rock and soil. At the same time, the Pacific Ocean has delivered a steady barrage of powerful swells. These long-period waves are generated by distant storms and carry enormous energy when they reach shore. Rather than dispersing quickly, they strike coastal cliffs repeatedly, focusing their force at the base. Elevated tides make the situation even more severe. When water levels rise above normal, waves reach higher portions of the bluff, attacking areas that are typically protected. This allows erosion to occur not only at the shoreline, but higher up the cliff face where stability is critical. Scientists describe this as a compounding effect. Rain weakens the cliffs from above. Waves erode support from below. Tides raise the impact zone. When these factors overlap repeatedly, failure becomes far more likely. Chapter 2. The hidden weakness beneath the surface. California's coastal cliffs often appear strong and immovable. But beneath the surface, many are built from materials that are inherently unstable under stress. Large portions of the coastline consist of layered sedimentary rock formed over thousands of years. Sandstone, siltstone, and mudstone are stacked in uneven layers, often separated by thin seams of clay. These seams can act like lubricated surfaces when wet, allowing sections of the bluff to slide. As waves erode the base of the cliff, they carve out recesses that undermine support. Over time, the upper portion begins to jut outward, creating overhangs that are held together by friction rather than strength. Rainwater intensifies this process. As water seeps into cracks and pores, it adds weight and reduces the resistance between layers. Eventually, gravity takes over. Blocks of earth and rock detach, sliding or collapsing toward the beach below. High-resolution geological mapping has shown that many coastal bluffs are already fractured and actively eroding. Under prolonged stress, collapse is not a rare anomaly. It is part of how these landscapes fail. Chapter 3. Coastline hotspots under surveillance. Some areas of California's coast demand constant attention because the risk is both high and ongoing. In Southern California, the bluffs near Del Mar are a prime example. These cliffs support a major rail route used by commuters and freight traffic. Over the years, repeated cracking, slumping, and minor collapses have forced emergency repairs and service interruptions. Engineers monitor this area continuously because the geology is particularly vulnerable. Soft, fractured rock responds quickly to heavy rainfall, and even small shifts can pose serious safety risks. Farther north, the Portuguese Bend landslide on the Palos Verdes Peninsula represents a different scale of instability. Covering hundreds of acres, it is one of the largest active landslides in the country. Movement here is persistent, driven by groundwater changes and seasonal storms. Roads warp, utility lines strain, and fresh pavement cracks soon after repairs. Entire neighborhoods exist within a landscape that is slowly, and sometimes rapidly, on the move. These regions share key characteristics: unstable geology, exposure to powerful ocean forces, and infrastructure placed close to an actively changing edge. Chapter 4: How Scientists Watch a Moving Coast. Monitoring California's coastline requires a combination of technologies, each designed to capture a different piece of the picture. Airborne laser scanning provides highly detailed maps of cliffs and slopes, revealing subtle changes in shape and elevation. These surveys can detect small shifts, but they are typically conducted only after major storms or at multi-year intervals. Satellite-based radar imaging offers broader coverage, allowing scientists to track ground movement over large areas. By comparing images taken days or weeks apart, even tiny changes become visible. However, this method includes unavoidable delays between observation and analysis. For more immediate insight, ground-based GPS stations continuously measure movement in real time. Some are positioned directly on known landslides, providing daily or hourly updates on how the land is shifting. At the most dangerous locations, sensors are embedded directly into the ground. These instruments track tilt, pressure, and subsurface movement, giving engineers early warning when conditions deteriorate. Despite these tools, one reality remains constant: exact prediction is impossible. Monitoring reduces uncertainty, but it cannot eliminate it. Chapter 5: When the data forces decisions. When monitoring systems detect accelerating movement, agencies must act quickly. Roads may be closed or reduced to a single lane. Rail service may slow or stop entirely. Utility companies prepare to isolate water, gas, or power lines if the ground begins to pull apart. In residential areas, inspectors examine foundations and slopes. If risk thresholds are crossed, homes can be red-tagged, requiring families to leave with little notice. These actions carry significant consequences. Detours can add hours to daily travel. Emergency response routes may be disrupted. Local businesses lose access, and entire communities feel the ripple effects. Yet officials emphasize that these decisions are driven by safety. A few centimeters of movement can mean the difference between stability and sudden collapse. Along California's coast, data does not remain abstract. It translates directly into closures, evacuations, and life-altering disruption. Chapter 6: What comes next for the edge? If storms ease and dry weather returns, saturated slopes may gradually regain strength. Some transportation corridors could reopen, offering temporary relief to affected communities. Even then, erosion continues quietly, reshaping the coastline over time. If storms persist, risk will rise. Each new surge of rain and surf compounds the damage, especially in areas already showing cracks and movement. The most dangerous conditions occur when heavy rainfall, elevated tides, and powerful waves coincide. In those moments, cliffs can fail suddenly, leaving little time for response. Past tragedies underscore this risk. Fatal collapses have occurred on seemingly calm days, driven not by a single trigger, but by years of gradual weakening. Today, more people live and work near the edge than ever before. As storms grow more frequent and sea levels rise, the margin for error shrinks. California's coastline is no longer a fixed line on a map. It is a shifting boundary shaped by forces that are accelerating. Monitoring provides insight, but not certainty. Adaptation, retreat, and hard choices lie ahead. The land is moving, with or without permission. Every tide redraws the edge. How communities respond now will define the future of life along California's coast.